Okay, let's start. A very simple way to do it is you just run it. Everything has been included in the folder. These are the functions that you aid the path so that you can utilize different functions. This one actually includes some tools like curve extraction tool and so on. Export fig, this is a library that I personally feel easy to use, that you can save high quality figures for publication purpose. This is a Morse wavelet, and this is used for continuous wavy transform, concentration of frequency and the time. And this is the main code of Synchrosqueezing. Okay, and this is a time series toolbox from the internet that you can utilize to generate different kinds of noises. And this folder database is just a folder that includes different types of signals and so on. If you open it, as you can see, there will be a very simple README, and which includes several descriptions of each data set, which I don't know if you have taken, take a careful look, but you can see there will be respiratory signal. Okay, and this is the electrocardiogram signal, which is purely electrocardiogram, but it has some very interesting artifacts that we will discuss later. BP is arterial blood pressure. Okay, and the A01 is transabdominal maternal ECG. PPG is photoplethysmography. Photoplethysmogram or PPG. Okay, and this IHR is actually instantaneous heart rate signal. This is the instantaneous heart rate of a patient that work from general anesthesia. This is general anesthesia. Okay. I hope this is easier to read. This is arterial blood pressure. Okay. Okay. And then this TA MECG is transabdominal maternal ECG. And this is the RR interval time series, which is another example of heart rate. So you can see there are several different types of data, but all of them are they're all time series. And there can be much more. And I plan to add more different types of signals, examples, so that you can play with. And students can also play with, but that is so far what you have. Okay, and then you can see there is a screen. This is just a parameter, which is very specialized to MATLAB, which doesn't contain too much. And then we run the code. And before we enter one by one, let's run it and do an interpretation of what we get. I just run it. I don't do anything. Okay, and then it generates a lot of figures, 11 figures. And what are they? First, this is the clean signal. Okay, and you can see the clean signal may have some, well, strange behavior, which oscillates in some strange way, which, well, I don't, just by reading it, it is difficult to see what's going on, right? You see, this is time axis, this is the magnitude, and it's oscillating. And the figure 2 is the noisy signal. You can see, if you look at the clean signal and the noisy signal, you can see they are very different. Okay, but that is how the signal looks like. And how the signal is generated, it is in step 0. And you can see more details about the description of the data generation in this paper, okay, which I put here. This is the original ConceFT paper published in 2016. It is recommended to take a look because this way of generating simulated signal, at least so far, is kind of relatively realistic because you generate a lot of randomness, but also fulfill the desired adaptive harmonic model spirit. And so the simulated data, simulated signal is challenging enough, but also simple enough. Okay, it's kind of in the middle. Okay, now the sampling rate is 100 hertz. This is a sampling rate, which means you will have 100 points per second. Okay, so in your field, depending on what the unit you use, the sampling rate may be different. What I care here, as an example, the sampling rate is 100 hertz since the time unit I choose is second, so that the sampling rate is 100 hertz. That is 100 times per second. If now what I care, the scale I care is minute. Okay, that is how many samples I have per minute. Then the sampling rate becomes 6,000 hertz. Okay, if what I care about a unit is kind of millisecond. In some applications, millisecond is the unit that you care about. Then the sampling rate is how much? It's 0.1 hertz. It's 0.1 hertz. Okay, because you only have 0.1 sample points, okay, per millisecond. And that is the time. And you can see what I sample here is I sampled 1,700 points, which you can check length of time. Okay, it's 1,700 points, which is time. This is n, the length of time. And then I just fix the random seed for the purpose of reproducibility. That is, if you don't fix it, you can still run the code, okay, but you may get a different signal when you do the simulation. And then this is the amplitude modulation signal. And amplitude modulation, I choose is to use a random process, smooth it, force it to be positive, and use it to describe the strength of each signal. This first one is AM1 is the oscillatory strength of the first component. AM2 is the strength of the second component. Okay. Yeah, and you can see here, I try to make some scene discontinuous. That is the first half of the amplitude modulation one is actually half of the size of its original simulation. Then this IF1 is the instantaneous frequency, which describes how fast the signal oscillates at each time. And then PHI1, PHI2, these are the simulated phase of each component. So we can take a look about what you are seeing. Suppose what is AM1? Okay, you can see that if I plot it in this way and compare it with the signal, okay, so maybe I need to enhance the lens. Okay, so this is clear. Okay, maybe I also want to put time so that you can see the time scale. Okay, so this is the simulated signal, which is a summation of two components. This one is the amplitude modulation of the first component. And this one And let me hold on so that you can compare. And I put it to be red so that you can see it. Oh, shoot. No, I will put it here. Okay, so this is the amplitude modulation of second component. Okay. And you can also check instantaneous frequency, like what I did before, and to do a comparison. This is kind of important so that you know what you are dealing with, because that is simulation. You have to know every ingredient inside it. This is plot time IF1 R. Oh, well, okay, so this is the instantaneous frequency, which tells you the signal oscillates slow in the beginning and faster in the end. And you can see it fluctuates in between 4 hertz to 6 hertz. Okay, and I can hold on and plot IF2, red. Okay, the second component oscillates slower. It oscillates 1 hertz in the beginning and faster in the end, about 2 hertz, but they don't overlap. Okay, there's a spectral gap in between. And you can make the signal more challenging by introducing spectral interference, instantaneous frequency crossover, etc. Okay, now this is amplitude modulation. This is instantaneous frequency. But there is nothing, none of this looks similar to the signal, so-called clean signal I showed you. Okay, so what should we do? Now I plot you the real intrinsic intrinsic mode type function, which is S1 and S2. These are the true simulated oscillatory component. S1 is the IMT function, intrinsic mode type function. S1, first one. S2 is the second one. Okay, so let's see how do they look like. This is T1, this is S1, S1. Okay, no color. Okay, good. So if you do a comparison, this is the first component is the blue one, right? It oscillates fast in the end and slow in the beginning, which is not that easy to see by naked eyes. But if you zoom in, you can see the difference. This is slower and oscillates 4 times per second, but this is faster. That oscillates about 6 times per second. And the amplitude, you can see the amplitude has a jump, right? From small to big. Okay, so this is the first component. And I can also plot the second component, second IMT function. So this is how the second function looks like. So let me, you can see it oscillates much smaller than the first component, right? And you can see first, the amplitude modulation is smooth, which is increasing, decreasing, right? And the instantaneous frequency is somehow increasing. So it's slow here and faster later. Okay, so these are 2 components. But what I showed you as the clean signal here, right? It doesn't look like the gray curve is the clean signal. It doesn't look like any of this. And what is this guy? This guy is actually, as we know, the summation of these 2 signals, the clean signal. So let me plot it again so that we are on the same page. Clean. And I'll use gray. Yeah. Color. And this is 0.7, 0.7, 0.7. Okay. And where are you? Okay, here. This is you. Okay. So this is simulated signal. And if I plot it in the same scale like this, you see That is the simulated signal, okay, that you can generate. Okay, so this is how the signal looks like. And now a very simple question for you, and what we care about in this non-stationary time series analysis is, in case I just give you this signal, then how much information can you say about this signal? Well, it is probably not that easy to answer, right? Suppose you say, hey, I am a big supporter of power spectrum. Maybe I can get something, right? I can try fast Fourier transform, right? Clean, and I can generate the this is okay. This is the frequency axis. And have xz times. Okay, good. Now I have a figure xc x hat. Okay, and two. Okay, suppose that is a power spectrum I have interest. Okay, but I don't take square. I just take absolute value. And shoot, A, B, S, yes. Okay, so this is kind of the power spectrum you can get. And let me enhance it. And this is 9 with 2, okay? And to enhance the reachability, you can see there is not too much remain after 15 Hertz. So I only show 0 to 15 Hertz to enhance the reachability. If you just look at this power spectrum, what can you interpret? There is something oscillatory at 2.5 Hertz, but what is 2.5, right? What is it? What is this point, right? 2.35 Hertz. Well, and there seems to have two peaks, right? What is it? 4.4, and what is this? 5.3. Oh, there may be another point spike. Well, it's hard to interpret, isn't it? So that is kind of the challenge of using traditional algorithm power spectrum to explore this kind of signal. Not to mention, well, what you really analyze is this noisy signal. This is the true signal you are analyzing. I generated this noisy signal. This is noise, and the noise is generated by some, well, maybe not so friendly way. This is ARMA 1-2 random process, which is stationary, but it has some peculiar behavior. And the first part, I replace it to be T4 random process, which is IID. But you can see that this noise actually is not stationary because the first part is it's kind of the first part behaves like student T4, but at time 6 seconds, because 600 points. After 600 points, it is the statistical behavior is changed to ARMA 1-1. Sorry, ARMA 1-2. So yeah, so it is kind of non-stationary noise, and this is a summation or noise contaminated noise. We can take a look about the noise. Let me see, noise time, noise, right? You can do the same thing. Nobody can stop you, and that is the noise. Okay. Okay, and if I ask you, hey, how much you can say about this noise, it is not easy to say too much, isn't it? You can say, well, maybe before 6 seconds, this has some behavior different from the second part, but there seem to have some, I don't know, blocks, clusters, but is it really true, right? So this is kind of the challenge you always encounter when you do the analysis. Now, how about if I say, hey, look, power spectrum is again our good friend. Yes, it is, and well, you may have challenge. It is maybe challenging to use it here, but let me see. Still, I want to see its power spectrum. And you can see its power spectrum is a bit peculiar. It has some strange spike at 25 hertz, but it's everywhere. But it has a strange spike at 25 hertz. Why? Okay, what's going on? Okay, this actually comes from the AR process, but it is not really a spike. It's not deterministic. So how to distinguish in between deterministic power spectrum and the stochastic power spectrum? That is another topic to explore. Okay, now finally we got our XM, the noisy signal. So we can again you see this is how the noisy signal looks like, right? How about this power spectrum? We can also take a look. Okay, so let's see. This is how the power spectrum looks like. Okay, and if we compare it with this one, okay, this is a clean. The bottom one is a clean signal. This is a noisy signal. If you are not aware of this kind of model business or not aware of the structure business, you may conclude that the signal has a very strong oscillatory component at 25 hertz. And this is totally wrong, isn't it? And you have some kind of maybe oscillatory component, several things, blah, blah, blah. But, well, that is not really correct. The truth is axis height. Okay, that is what you can see. You can compare, right? You see the clean signal, or the clean deterministic signal doesn't have anything here. And certainly we can continue the discussion from the perspective of identifiability and so on. Why do you prefer to model things in this way but not another way? But that is another topic. Okay. Anyways, so far that is about signal, which I spent about 10 minutes. But I think it is a good thing that you can take a look at the signal and try to practice it your own. You know how to observe the signal, and the signal is generated by me, simulated by me, so I know everything. Okay, good. So I will close the signal, those power spectrum which we do not need, and this is what? This is noise. I don't need it. This well maybe this we can keep. Okay, very good. Now, second part of the code, after generate the simulated signal and plot it. These are what I used to. Oh shoot! Sorry. I hope I didn't screw anything. Oh yeah. No. What? This is the same. No, this is not what I'm talking about. Okay. Yeah. So this is how I generated signal, and you can uncomment this code and try to save the signal and try to save the figure and so on and play it, and you can play it on your own. Now you can run different time frequency analysis tools, and there are some papers you can take a look, and I should put some more papers here. For example, the second order Synchrosqueezing transform, and so on. And I will put more here. But this is just the first one is the original paper of Synchrosqueezing, or the first theoretical paper of Synchrosqueezing transform. This is the statistical paper describing the asymptotic behavior of Synchrosqueezing transform. And this is, well, another paper describing the robustness of Synchrosqueezing and so on. And there are several other algorithms that we will use, like, for example, the ConceFT algorithm. And this is, or the original Synchrosqueezing is just use the first order phase information. And if you use the higher order one, you will get higher order Synchrosqueezing transform and so on. And Here, there are several parameters, and I will not explain them in detail, but you can play with them. Everything is commented here. For example, for this part, these two parameters, they are utilized for concentration and the frequency and the time, which I remark here. If you want to run ConceFT, you can say, okay, let's choose two windows, two Hermite windows in this parameter. That is how many Hermite windows you choose. And the NO concept, that is how many samples in the sphere you want to use, how many non-orthogonal windows you want to generate concentration, frequency, and the time. And this is for details, you may want to take a look at this paper. Okay, so this is the original paper of ConceFT that you can take a look. Okay, good. Okay, and this is the window. This is the kind of the main key parameter in synchrosqueezing and the most time frequency analysis. Okay, so let's take a look at the meaning of this window length. This is utilized to generate the length of the window when you apply short-time Fourier transform, synchrosqueezing transform, ConceFT, etc. And even the D shape we'll discuss later. And what is it? It is actually the window length that you use, for example, not violin. I have, yeah, here. For example, this is the code we generate the Hermite window. So Hermite function, and this is a number of points you want to generate, 577. In this case, I will explain 577 and its meaning and how to choose it in a bit. Now I can say 2. Okay, suppose I want to generate 2 Hermite functions. 10, this is actually the truncation, decay truncation. Okay, that is how wide the window should be. Now I can put the h, which is a derivative of the window. This is the time related to the window. Okay, so this is how I generate the window. Of length 577, and if you remember, I have sampling rate 100 Hertz signal. So 577 means the window length will cross 5.77 second. 5.77 second. And this is the bandwidth, window bandwidth, like how fast the window should decay. Now, you can take a look at figure, plot TTTH. And let me shoot. Okay. And then this is how the window looks like. Okay. The blue one is the first Hermite window, aka the Gaussian window. The red one, okay, is the second Hermite window, which is a window that is orthogonal to the first Hermite window or Gaussian window with related to the Gaussian weight major. Okay, so what you can see is this is minus 10 to 10. What it means, this 10 comes from this 10, which controls, if you choose 20, then you will truncate the Gaussian window somehow at 10 seconds or 20 seconds. If you choose 10, it's 10 seconds. If you choose 6, it's 6 seconds. If you choose 10, it is 10 seconds. For example, you can see another example. Usually we use 6 or 8 or 10. And then I plot figure, then this is how it looks like. You see, it becomes somehow wider, but it's not really wider, but because we just do the truncation at different time. But the impact is, if you apply this window, 577 seconds window to the signal, you do the truncation at different rate. This one, you truncate a shorter segment because it decays very fast. This one, it truncate out more signal so that you run the algorithm. So that you have because you have a wider, slower decay. Okay, so that is the impact of window, and you can play with it and see how it how it changes the result. And to fully understand it, you have to dig into the code, how the concept or Synchrosqueezing or is ran, and we will come back to this later. So the key question is how to choose this parameter. This is always the key question. This is a very important parameter, as I said about 3 minutes ago. How to choose it? I mean, usually the rule of thumb is if your signal oscillate at let's say 1 hertz. Okay, that is you have the signal will have kind of roughly 1 oscillation per second. Then usually we want to choose the window so that it covers about, let's say, 8 or 10 cycles. Sometimes it can only cover 6 cycles or even shorter 4 cycles if you only have one component. But if you have multiple components you want to analyze in the signal, then it is better to choose a slightly longer window. If the signal is actually quite noisy, then you want to choose an even longer window. That is maybe cover 15 or even 20 cycles. So what is how much do you know the oscillation inside the signal? That is actually a chicken and egg problem, right? If I just give you a signal that you do not have any prior knowledge about, well, how fast the signal oscillate at which time and so on, then how can you choose the window? Then well, in practice, if I'm working with a field that I have zero background knowledge, this is something very challenging to me. But for the biomedical signals, usually we have some physiological background that we can utilize to, to guess how long the signal how long the window you should choose. But in the end of the day, how to automatically determine the window length for a given signal. This is a quite challenging problem, which needs more research from a statistical perspective. So at this moment, I don't think there is an automatic way to, I should say there are some, but if you want to say if there is a satisfactory automatic way to choose this Windows lens, I would say not really, but there are some publications, and I will tell you. For example, I myself had one paper in this direction, but where is it? I don't remember. It's kind of wait, hold on. I shouldn't do it on the spot because I don't remember it. Where is it? But anyways, J, hold on. Now I want to find it. So, okay, this one. Yeah. So this is the paper that you can use entropy-based way to find the window, the optimal window. Okay. So, but again, it works, but I would not say it is a satisfactory solution. And also, we do not have a theoretical guarantee about that choice. Okay, now this is sampling rate, just the input to the signal. And now this is another parameter that is very important, but that's easy to understand. This is only, and I have put all the statement here. Actually, what we do is we viewed when we implemented the code, and the code is actually a modification from Professor Patrick Flandry's original code. So we just follow his convention. And this is also another convention seems to be in electrical engineering. They usually view the sampling, the data sampling is at 1 hertz, and we do all the analysis at 1 hertz, and you scale things back. So that is why if sampling rate is 1 hertz, and by the signal processing theory, the highest frequency you can observe is 0.5 hertz and so on. So this is what I meant. You assume the signal is sampled at 1 hertz so that you get the information from 0 to 0.5 hertz. Then you scale things back. That is the true final spectral range you are doing because you scale things back by the sampling rate. Okay, and this is just the resolution you want to see in the frequency axis. And hub is one simple way that you can speed up the calculation of synchrosqueezing. So usually, if you are not interested in see so dense and so dense information in the time frequency representation, and you want to speed things up, you can apply hub. You can increase the hub. For example, if you increase hub by 10, then the computational time is reduced by 10. Why? Because you calculate the time frequency representation every hub samples. And the hub 1 means you calculate the time frequency representation at each sample. And if you choose 10, if you change this to 10, suppose you change this to 10, then you calculate the time frequency representation every 10 samples, meaning in our case, our sampling rate is 100 hertz, and you have hub 10, 10. Then it means you generate a time frequency representation every 0.1 second. Okay, and we'll come back to this in a bit. Now this is the code. And I just show you two. This is the noisy data. This is a clean data, noisy data, clean data, okay? And then you just input since all the parameters are here, and you get TFR. Okay, TFR or TFRC, that only means the output of clean and output of noisy. TFRC is the short-time Fourier transform result. TFRC, TFR tick, that is the y-axis, the frequency axis of the short-time Fourier transform. This is synchrosqueezing transform. This is concentration of frequency and the time concept. This is the frequency tick of short-time Fourier transform and the concept. Okay, and the final parameter actually gives you the reassignment rule, but I don't show it here. Okay, now you can finally plot everything. So let's take a look. You should get what? This is okay. So well, yeah, okay, 3. Yes, this is a short-time Fourier transform or spectrogram. That is the absolute value of the short-time Fourier transform. And again, I don't take square here, but so just still call it spectrogram. This is figure 3, short-time Fourier transform, and this will just move them. And this is 3, 4, 4. Okay. And this is what? This is the synchrosqueezing transform. Okay. Result of this noisy signal. Now, this is what? This is okay. Oh, shoot. These two are repetitive. Okay, I'll change it in a bit. This one is a synchrosqueezing transform of the clean signal. This is a clean signal synchrosqueezing, okay? And this is noisy one. And now let me change 6. This is SST. I want, hold on. I should have, this is a spectrogram, noisy, and I should have a spectrogram of clean. Give me a second. I want to show you clean one so that you can do a comparison. Now, where are you? This is here. Yeah, now we are here. Good. And this is really repetitive, so it's not necessary. I have this one and this one. Okay, good. Okay. So you see, this is the clean signal. And if you run short-time Fourier transform, you can see quite a lot of spectral interference here. You can see there are several vertical lines. these are spectral interference, okay, here as well. Okay, and but if you go to the short-time Fourier synchro-squeezing transform, this spectral interference, the spectral interference is still there, but you have to read it very, very carefully so that you can see it. And moreover, you can see the spreading is kind of be more concentrated, and this will give us a lot of benefit when we do signal processing, like curve rejection, ridge extraction, and so on. And this is a noisy result, which you can see a lot of strange background. And if you remember, the first part of the signal is actually quite noisy, and the second part is less noisy, although it may look a bit weird. Look how to like when you generated the noise, actually the first part is non-stationary compared with the second one, but we do not really see any noise trends issue, right? Well, it is kind of the second part is maybe, well, it's hard to say. Okay, why? That is because of the spectral properties of AR process. Here, you see, it looks like around 0 to 10 hertz is quite clean. It has quite clean background. It is because the noise is concentrated in high frequency region because of the nature of this AR process, which if you know some autoregressive process, you may be able to appreciate it. But what I want to say is this is because of non-stationarity of the signal, so that it seems that the first part is more contaminated and more noisy, but actually it's not the case. Okay, but no matter what, from all these figures, you can see all the truths. Now, what is the truth? Okay, here. This is the ground truth. This is the ground truth. Okay, I just superimpose the instantaneous frequency of the simulated signals. Now you can see they look quite similar, isn't it? They look quite similar, isn't it? Okay, very good. So that is how you generate the uh, the Synchrosqueezing transform figures and so on. And let's stop here. We will continue maybe next time.